Hello, everybody. Welcome. Oh, shoot. Oh, shoot. I don't have my... Sorry, guys. Just give me 1 second. Hello. We're back. Sorry. Usually I watch the whatever task doing on my cell phone here, and there we go. Muffle. Can you hear me now?
Hello. Testing. Ah, jeez. Good lord. Where am I? Okay. So, not sure why that's happening, but, well, missing my little dongle for the... Alright, anyway, sorry guys. We are resuming with everything. Hello. Yes. McMaster University and the course of CS1MD3 would like to apologize for the technical interruptions which were occurring during the first 3 minutes of this lecture. We will now proceed with the topic at hand. So, that's all right. Where did the frickin' slides go, man? Good lord. Give me 1 second. Okay. All right. We have the slides. This is good. Okay. Sorry about that, folks. Sort of through the mystical operations of a universe we don't clearly understand, the slides were delivered to me not 5 minutes ago. So, yeah. I've been having the TAs sort of, a couple of them, redoing the slides to make them look better, and I really wanted to roll them out tonight, so... Alright. So, to the question regarding the person who renamed Assignment 1, it does say to not do that right at the top of the assignment. Tell you what, though, since this is the first time, shoot me an email about it and we'll take care of it privately, alright? Good. Yes. Terribly sorry about the sound quality. I'm having to do this from my laptop's microphone rather than my special, headset encased microphone, so you get to see how the entirety of my head looks like today. Anyway, so might as well move. Oh, thank you. My goodness. You know what? Having a significant other is the best thing ever, because they can find things for you while you're on stream. Alright, this is the thing. all right? It takes this stupid jack, which is a compound jack, and makes it into both an audio and a microphone. I usually only have the microphone plugged in, but this is the manner in which, like, it doesn't work if I just plug the compound jack into the microphone port for whatever reason. You need the little splitter. Anyway, all right. Man, this has been a rough lecture so far. I will try to improve. So, today we're going to talk about statements. We're going to make a statement. Har har. So, with respect to programming, when you're programming, you're typing things out. When you're typing things out, there are particles of speech in the same way that when you're speaking or you're typing out a paragraph. Statements can be likened to the sentences of a paragraph. They are self-contained units that contain information about what to do. Of course, imagine, yeah. Thank you, chat. We have named the cat, actually. We've named the cat Marimba, after the musical instrument, because she's got such a jazzy personality. Very cool cat. Anyway, so when you're typing out a program, basically statements roughly align with each of the lines of code, at least in something like Python. So, but that's, generally speaking, that's a pretty good convention. So, so generally speaking, okay. This is, we have a table of contents slide now. Very exciting. These chapter titles are placeholders, I suppose. Anyway, we spoke last week about structured flowcharts. This sort of idea that the flow of information through a program can be characterized in a graphical manner, and we start off with these simple ones like boxes. Boxes are just simple assignment statements, right? If you remember to last week, something like x is equal to 3, that's one of these rectangles. If you want to do more complicated stuff, then you've got a slightly more lines going on. So if you want to start doing things that are complicated, you start needing these diamonds. The diamonds indicate a conditional, right? They indicate a branch. So you have some condition, B in this case, and if that condition is true at the time that the program execution reaches that statement, then you travel along the yes or true branch. Otherwise, you travel along the no or false branch. Percussion, yeah. So, in the case of a regular if statement, which is this one right here, if B then S, you can see we have the program execution flows into the conditional statement. In the case that it is true, we travel along the yes branch, execute the statement S, and then continue on. In the case of N, or no or false, we just skip it. We just keep on going. Actually, Ethan, that's a good question. How are the tutorials going to work tonight? Generally speaking, in much a similar manner to the lectures. The TAs, everybody should have a section assigned, and the TAs are going to be going through separate exercises that are external to the lecture slide material that we've been doing so far, sort of adjacent to it, if that makes sense. The expectation from my side is that as that tutorial is going on, you are plunking away on your computer, creating the same program that the TA is showing you how to create themselves. It also provides you an opportunity to ask the TA questions about assignments or the material that we've been covering so far or anything like that. Today, the tutorial is going to be Number Game, which is a very classic tutorial example for programming. Actually, the Number Game was one of the very first real programs that I ever learned in my life when I was a young lad. My father had somehow obtained an Apple II, which was a very old computer even at the time, and I had a book on how to program video games in BASIC, and that was one of the first video games they had on how to do it. How do you find your assigned section? It literally doesn't matter. Check the syllabus and pick one. We're not taking attendance or anything. So anyway, so with respect to if statements, we also have the branching if statement. So, or the to-branch if statement. In the case when you have something executing on this branch that was just skipping S before, that's when you start talking about if then else. So if B, I do this. If not, I do this other thing. Reasonably simple. And of course, we also have repetition. Repetition is looping. Looping is it should be the first real conceptual hurdle that you will probably face in this course if you have no experience with programming. Loops are a little bit tricky. They're not impossible, certainly, but they're a little bit tricky. So to the question, is tutorial just basically an allotted time to work on assignment with help from TAs? About half of it is that. Half of it is a exercise which has been prepared. So, as I said, in this one, they're going to show you how to make the number game. Yeah. So, anyway. That's just a reminder about flowcharts. So here are some specific applications of these flowcharts to Python. In the case of a straightforward if statement, to represent this conditional, you type if B : If you want to do, when you type the statement S, you tab over. The tab over is extremely important. And then you type S, or whatever S is, the statement that S is representative of in this particular case. So, yes. In the case of the to-branch conditional statement, we have if B then S, which is exactly the same as in the other one, to indicate that there's something to do along the false branch of this conditional statement. You type else, tab over, and T. In the case of repetition, you say while B, S, where you tab over S. So I'll talk about the tabbing just for a moment. Python is a bit of a unique programming language because white space is important. In a lot of other programming languages, the way that they indicate what is inside of the true branch of an if statement is indicated by curly braces. So if you were programming in C, C#, C++, any of those, Java, I think, uses the same convention. Lots and lots and lots of, programming languages use that convention. In Python, things are a bit different. It is indicated what is inside of an if statement, or a while loop, or a function for that matter, by the indentation. So this follows along from a convention in other programming languages, but it's not a strict requirement. So let me just open up a brand new, which might have something in it though, Python workbook, notebook in my own local Jupyter instance. I will show you. So in a program like C, what you would have is if B open brace, close brace, and then you would have the statement S, right? It doesn't actually, well, you also have to have a semicolon in something like C because that indicates the end of a line. But it's not actually necessary for you to type like that. In C, you can actually, it's equally syntactically valid to write your expressions like this. In fact, you could write a whole string of statements like this. And you'll see that this actually looks quite a lot like the compound statements that we have in Python. However, this is a very difficult way of understanding what your code is saying. It can get very long very quickly and is, generally speaking, considered a bad way to code. Generally speaking, the convention is to put each of your statements on a new line. Like this. However, in Python, one of the design decisions that they made when they were creating Python as a language is to try to reduce the amount of miscellaneous symbols that are required to program. This makes it a little easier to pick up for someone who hasn't done programming before. So what they did was they said, okay, so this is the convention for how something inside of an if statement looks. First of all, let's just remove all of these semicolons because it's tedious to have to type them at the end of every single statement. We're going to make the new line implicitly the end of one statement and the beginning of another. So we know that S and A are different statements, not by the fact that there's a semicolon in between them, as would be the case in most programming languages, but by the fact that they're on different lines. This is a very, it's fine. It's a completely valid way of doing it. It does minimize the use of extraneous semicolons. However, it does mean that new lines become important, right? So there are some things that, well, I was going to say there are some things that you can do in C that you can't exactly get away with in Python, but, it's most of the time Python's pretty good at picking up in those cases, actually. So that was simplification number 1. Simplification number 2 that they performed was they said, you know what, these curly braces, they're just, why would you need to type 2 characters? That's way too many characters. Let's replace them with a colon. Colon, generally speaking, denotes a list of things in the English language anyway, so let's use it for this purpose. So, this is fine, except this basically has the effect of canonizing the indentation scheme that is it's a convention of other programming languages, but not a requirement. In Python, it is a strict requirement. If you say, if you take away the indentation from one or more statements inside of Python, this means, like the way that I've done this here, E is no longer inside of the if statement. It's no longer in S on our flowchart here. It is somewhere along this branch here. The program will continue on and hit E once it's finished with all of the B and S stuff that it's dealing with. So, and I know that I might be, like, for some people I'm probably hammering home a point that's, relatively, not terribly difficult, but it's really, really important if you don't understand this to understand this. The same thing applies to, for example, function definitions. So if we define some function, the same thing applies. So we have to change our tabbing accordingly. So if we want D and E to execute after the if statement, they have to be tabbed out of the if statement. And if we want all of that to be inside of this function, sumfunc, then all of that has to be indented by at least one level. And in fact, inside of this, it's permissible inside of Python. You can define functions within other functions. Boop, like that. And then the way that you tell what's inside of this function is by the fact that it will be tabbed over twice. So the tabs are super, super important. I can't underestimate. I cannot express sufficiently using mere words how important it is to understand that tabbing puts things inside of other things. Same thing as with while loops. So anyway, I'll stop banging on about that particular point and we can move on. So, yes, Python uses indentation for grouping nested statements. Thank you. So, let's talk example. Factorial. For those of you who may not be familiar with the factorial from your high school combinatorics class that you may or may not have taken, the factorial of a number is basically all of the numbers up to that number except 0 multiplied together. So if you have the factorial of 7, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. So, a way of expressing this mathematically is n factorial is equal to 1 if n is equal to 0, and n times n minus 1 factorial for n greater than 0. So notice that this is a recursive definition. We're going to get to recursion later on in the course, but basically the first pass approximation of recursion is a recursive definition is any definition which includes itself in its own definition. Which, you know, in other fields of human knowledge, that would be called a circular argument. However, in mathematics, it works into the idea of induction. So what an induction is it's comprised of two parts. You have a so-called base case, and you have an inductive step. So this definition that we have for factorial, it's okay as a definition because it will eventually, in computer science we would say it would eventually terminate, i.e. eventually you will reach a case where n minus 1 is 0, right? So, and you know, technically you could stop at 1, not 0, because it makes no difference because you're multiplying 1. But anyway, if you start at n factorial of 5, for example, it would be 5 times 4 factorial. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial, etc., etc. Eventually you'll hit 0. And then it's no longer self-referential, which means that you can just say, okay, then we can collect everything up and recalculate it. But anyway, yes, so in combinatorics, the factorial is used to count all of the unique permutations of something. For example, there are 5 factorial ways of rearranging the letters of A, B, C, D, E. It's actually the number of permutations is equal to the size of the number of things that you're permutating. So let's create a program. I'm going to actually, you know what? Let's do this in code. All right. So define a function, factorial. In order to write a function, we need to know what the input's going to be, and we need to know what the output's going to be. In our particular case, for factorial, we are taking some number. That number is going to have to be greater than or equal to 0, but we'll worry about that a little bit later on. So we're going to define this using a loop. We're going to use a loop to be able to count out all of these numbers that have to be multiplied against each other sequentially, rather than having to write it out ourselves, right? So you can imagine if we had to do this by hand each time, it would be extremely frustrating. Like return 5 times 4 times 3 times 2 times 1. That would, like, first of all, you don't know when to start and when to, you don't know what number to start at. And second of all, that just takes too long. We don't like to work that hard. So we define a loop. We will keep an accumulator. So result is equal to n. While n is greater than or equal to, greater than will work, 0. Result is equal to result multiplied by n. Then at the end, we return result. Just for the sake of argument, I'm going to have it print n. N is equal to string n. Don't worry about that, we'll get to that sort of thing. This is just for the purposes of display. Result is equal to, I have to concatenate that actually, string n. There we go. So we know everything compiled because I ran that cell and I didn't get a syntax error. So I'm sure you guys had plenty of syntax errors when you went and did assignment 1. Don't pretend you didn't have syntax errors. There's no shame in it. I myself make plenty of syntax errors. But anyway, if we want, we should print the factorial of 8. So you can see, oh, aha, we have a problem. I may not have made a syntax error, but I made an error of a different kind. However, this is very instructive, so we'll just stop that now. So I have fallen into one of the very, very traditional traps when making a loop. You'll notice that n is never changing here. I have not put into this loop any specific statement which modifies n. Therefore, n is never modified. The result never changes. However, it is somewhat curious that the result isn't changing either. We'll have to look into that. So this is becoming a, yeah, exactly. Yes. So let's fix the infinitude of the loop first. So every time we execute this loop, we want to reduce the value of n by 1. So let's reload that function and see what we get. Oh, I see what I did. I was not printing the result. Ha! There we go. So now you can see when n is 8, our result is 8. 7, 64, 6, etc., etc., etc. Then until we get our final result, 322,056, or 56, 560, pardon me. And if you pull out your handy-dandy Casio calculator, you can verify that result right now, as I am doing. Ooh. Well. It's wrong. Interesting. All right. Why would it be wrong? That doesn't make any sense. Yes. All right. Oh, 7 times 7 is 49. Is this just multiplying by 7 each time? Is it just multiplying by whatever? Huh. Now that's silly. So this is programming for you guys. Yeah. So this is kind of the reason why I tend to, every once in a while, throw in these examples where I throw a bunch of code up from scratch. It's in order to indicate, or in order to show you guys that even someone who ostensibly has a reasonable degree of programming skill, such as a person teaching a first-year Python class, I also have to debug my code. And it's also illustrative to show, if you see how I solve a problem, that can help you figure out how you can solve problems too. Put n-1 in the line prior. Let's see. That probably will work, yeah. So, according to my calculator, 7 factorial should be 5,040. However, that's not what we're getting. So 7 times 6 is 40. Oh, what? So 7 times 6 is 42. So this result right here should be 42, which is interesting. No, it's true. N times n-1? So in the first iteration, we've got 7, right? Going into the loop, n is assigned to the result. On the next iteration, we should be going before it was like this. Let's see what we got. Another thing that you can do when stuff like this happens is you can put all kinds of print statements all over the place to see what is going on inside the code itself. So, interesting. And now we're getting the correct result for some reason, except on the last iteration where we're going to 0. So we actually have to do that. There we go. Okay. That's the correct result. So part of the advantage of programming is that you can throw a solution out there, type it up, see if it works, and if it doesn't work, you can make little tweaks to it in order to try to pull the correct answer out of it, and then hopefully it'll be correct for other answers too. So, in this particular case, we decremented this guy before we feed him into the result. As a result, when the result is 7, we are multiplying against it, n is equal to 6, and then 5, 4, 3, 2, 1. So we are not remultiplying a number that we already had here, which some of your more astute colleagues have indicated. So, yes. Oh, and yeah, if you're going to do something like that, obviously subtraction binds less tightly than multiplication, so you have to put it in brackets. But that'll work. Anyway, yeah, so anyway, that's factorial. here is an implementation of that as it exists in the lecture slides. You can see it is reasonably similar to the one we came up, minus the print statements, of course. If we take out the print statements and sort of tighten it up a little bit, you get something very similar. The only difference here is that where I'm applying the decrement operation to the argument that's provided to the function directly, which is kind of bad form, to be honest with you, they are, the slides are using an independent variable I. So there you go. So the other point of this is an illustration of scope. So with this whole function, if I put everything in the same block just for a moment, if I try to see what the value of this result variable is after finishing the execution of Factorial, I get this error: name result is not defined. Will the update to the slides be going up tonight? Should be yes. I think they will be yes. So if not tonight, then first thing tomorrow morning. I don't know, this whole thing, like 8:30 is It's a matter of if I can keep up the energy. Oh, just kidding. Yeah, sometime tonight I'll put them up. So this result variable, this only exists within the context of the factorial function, right? So if I defined a function after, or if I defined a variable after this function, like x is equal to 7, right? And I put x in there, and I asked for the result of x, you can see that x has not been modified by having passed through this function, even though we're directly modifying it. This is because, this is because Python uses a thing called pass by assignment. So whenever there is a passing of something into a function like that, Python is implicitly saying, okay, I'm going to do this without you seeing it, and now I'm going to execute all of the rest of this code. All right, so x in turn is not modified, but the result here, that does not exist outside of the function. That's scoping for you. This is a local scope. Inside the function is a local scope. Outside the function is global scope, roughly speaking. So this is the version of the same thing, but without using the multiple assignment operator. You can see they are using the commas here to do multiple assignment, which is, you know, just a slightly more compact way of doing it. This would be closer to the way that we were doing it, with a different statement on every line. This is another alternative way of doing that. You can see we're using semicolon to separate individual statements here. This is, again, 3 ways to do the same thing, basically, whichever your preference is. I'm just going to check the chat quickly to see if there's anything. Yep. A lot of people correcting my programming. So, yes. So in the same way that okay. So in contrast, actually, to the version that we did, these versions that we've been looking at if you notice, these are actually counting up rather than counting down. Notice the thing that's counting, I, starts at 0, goes up to 1 less than n. In our version, we started at n and went down to the value of 0. So, this should be an illustration to you that both of these methods are equally valid means of attaining the goal. Counting up, perfectly permissible. Counting down, also perfectly permissible. In this particular application, it doesn't matter because multiplication is associative, or it doesn't really matter which order you do multiplication operations in as long as they're all multiplication operations, right? It won't affect the final result. So you can count up, you can count down, they both have the same effect. So this is the decision to start multiplying with 1, 2, or 3 is arbitrary. We can equally start as well with n, n minus 1, etc. So, and then we come around to the actual version that we did, which is by modifying the function parameter itself. So here's a little bit of nomenclature for you. This is when you're invoking a function, this x is called the actual parameter. And when you are defining a function, these are called formal parameters. You'll also often hear me call these arguments. All right? So actual, because that's the thing that's actually getting passed in. Formal, because, formally speaking, it's really properly called n. But anyway, it sometimes trips people up a little bit if x and n happen to be named the same thing. So if we, for example, have an n here and an n here and an n here, don't make the mistake of imagining that the actual parameter and the formal parameter are the same thing. They are not. Because they are scoped differently, the globally scoped n will take precedence in a globally scoped environment, and the locally scoped n will take precedence in a locally scoped environment. Technically, everything that's global is also accessible locally. We'll get into it. But inside the function definition, it's talking about this, the formal parameter, and outside of that, it's talking about the actual parameter, even if they're named the same thing. I have a question. Would it be better to use a for loop for this question, since you would always go consecutively to 1? It's generally better to use a for loop for most things. If you want, we can do a version of this using a for loop relatively easily. We haven't quite gotten to for loops yet. There's a... Oof. I almost sneezed there. So, we're going to be getting to for loops by the end of the lecture tonight, but here's a little sneak preview of what it would look like. So, well, you'd still need the accumulator. Result is equal to n, or actually, let's do it as 1 for range n, or for x in range n, result, I'll show you this one. That's multiply equals. It's basically the same thing as result is equal to result times. It's just result times equals x, return result. And let us see if factorial 2 produces the same result. It does not. Oh, come on. Oh, because it would be including 0 in this. So we'll do it from 1 to n. Here. Minus 1? No, that won't work. Well, anyway. Okay, let's try here. See what we're doing here. 1, 1, 2, 3, 4, 5. So we're stopping 1 early. Okay. This is good. Oh, right. So the range function, the way that it works is it creates a range from 1 to n minus 1. So if we actually want n instead of n minus 1, we have to put n plus 1. And there we go. We get the correct result. There we go. And that is a little bit of how you use for loops. So the primary advantage of a for loop, you remember how at the beginning I forgot to do the n equals n minus 1 statement? Notice that that doesn't actually exist in the for loop. So the for loops are generally speaking a manner of going through every element of an iterable data structure. The range function creates an iterable data structure using numbers from, in this case, 1 to n plus 1 minus 1, which is, of course, n. And then we multiply everything in that to the accumulator, and Bob's your uncle. And you can see that the primary advantage of using a for loop is that we have saved one entire line of code. My goodness, it must be more efficient. It's shorter. Anyway, so again, to go over the thing that I said earlier, Python uses pass by assignment, which means that the formal parameter n, as it's being executed by the inside of this function, that's not doing anything to change what was passed to it as an actual. Okay, I have a question. When can we fetch feedback for our assignment? Excuse me, it will be emailed to you. So you don't have to go fetch it. You just have to wait for it to drop into your inbox. And the answer to that question, the answer to going to get the feedback from assignment 1, I am going to get on Swale tomorrow morning and see to it that he has those out by the end of the day tomorrow. If you're listening, you're on notice, Swale. Okay. He's a really good guy. We joke. So, anyway. So, again, it's slightly bad form to modify the parameters that are, like, the parameters that are provided to the function. And this is for very sort of hand-wavy general reasons. You notice I was actually waving my hand as I was saying hand-wavy. So, in languages other than Python, it's not necessarily the case that there's a separation between actual and formal parameters like that. Sometimes modifying something inside of a function actually does modify it outside of that, actually does modify a variable that was provided as an argument. Depends on the language. Safest thing to do, just copy it to some new memory, operate it, and then output what you need to output. Sometimes this is even true within Python. Later on in, I think on Wednesday this week, I'm used to saying things like next week. On Wednesday this week, we're going to be talking about data structures and mutability. And when we talk about mutability, we're going to get into how sometimes, in the cases of mutable data structures, a data structure can be aliased by another variable. So it's not that there are two data structures. There are two variables that both point to the same data structure. And if you're in a situation like that, modification of that data structure within a function will, in fact, modify it everywhere, not just inside the function. But, you know, we'll get there. Give us time. Anyway, so It is currently 6:21. We will have our first of 2 breaks. Talk to you all at 6:30. I can't believe I did it twice. That's terrible. I am so sorry. Anyway, let me try again. Oof. So, with respect to counters and accumulators, this next chapter is a couple of auxiliary things. I was just commenting on how nice I thought this heading was with all of the individual sections, so you can see how far along you are, and especially since slide pages no longer match up to like slides because of the pop-in. So anyway, with respect to the manner in which we were structuring, yeah, my God. My goodness. Oof. Oof, yeah. Anyway, with respect to these previous examples that we had with Factorial, I'm sorry, guys, I'll get better at this as time goes on. Still getting used to the whole taking breaks thing. Anyway, with respect to the Factorial examples, we had a pretty clear counter and accumulator. I was the counter, F was the accumulator. I was doing the counting, and F was doing all of the multiplications operations that served to construct the answer. So, generally speaking, if you don't modify the counter, you'll get an infinite loop. But if you don't modify the result, you'll just get a wrong result. That's yeah. Thank you. I love you guys too. You're awesome. I appreciate it because, you know, ordinarily I'd be having all of these goof-ups in person. You know, I'd still be goofing up, but at least I'd be goofing up in person and we could all have a laugh about it. You know, there'd be a silent chuckle that would run through the class whenever the prof did something especially goofy. But now I can't even see if you guys are chuckling to yourselves or if I'm just being frustrating. Anyway, that's part of the like, I know the chat, like chat, I love you guys. You guys are great. But like, there's really a strong difference between this and, you know, doing this live to a live audience. I really hope that we can move back to doing this in person again, like, very soon, because, I don't know. Not my preferred way of doing things. Anyway, so with respect to a counter, they can count up, they can count down, as we saw previously. We are starting to think about things like upper and lower bounds. What is the range inside which we want to count? Generally speaking, the accumulator should be initialized to something that is correct if the loop is not executed at all. So when you write a loop, you want to write the loop in such a manner that if, like you always plan for like 30 executions or 50 executions, but you should also always plan for 0. Okay, so in the case of the factorial, if we go back to our definition of the factorial, if n is equal to 0, which would be 0 iterations in our case, we want our value to be 1. So, in this case, our accumulator should be initialized to 1. There you go. Very cool. So, here's a question. What does this code output? Def sum. I is equal to 0, s is equal to 0 as well. While I is less than the length of t, which is a tuple, which we talked about at the end of last class, s plus equals does the same thing as multiplication equals, except with plus, t at I, return s. So, if we have t is equal to 5, 10, 15, print the sum of t. What'll that say? Is it A, 15, B, 30, C, error, or D, nothing? I will give you guys a moment to catch up to the fact that the stream is happening 30 seconds into the future. Aha! Yes. So, we have some clever clogs in the audience who have realized we are not actually modifying our index variable right here. So, this will be an infinite loop. Now, the thing about an infinite loop is that it doesn't cause an error. That's what it does. It just means that your program takes forever and does nothing. So technically speaking, you could do either of these. It would be correct in one sense to say it doesn't output anything, because on a hypothetical infinite computer with infinite system resources, it would just literally take forever to not do anything. However, on a real physical computer system, then this program would run until the computer system itself failed, right? Which means it would fail with some error, which may or may not be related to the program that's currently running. So really, C or D is correct. If we had added the index modification statement in a correct manner to make this not an infinite loop, then we would have gotten B, 30, because obviously this is summing all of the elements of the list, or the tuple. Sorry, we're going to get to lists. So, if you get an infinite loop, there are a couple of things you can do. On Jupyter, right here. Whoop, that's not Jupyter. Wah, wah, wah. There we go. So, if I just, oops, I accidentally commented out the thing that makes my program terminate. I wonder what I'm going to do. I'm going to cause an infinite loop on my computer right now. So, the way that you can tell that you're in an infinite loop is that you've got this star icon in these square braces right here. If it's generally speaking, this is like this counts the number of cells that have been executed since the workbook was opened. So this star means currently calculating. So this is right now in an infinite loop. There are a couple of ways to fix it. Number one, hit the stop button. That interrupts the kernel. Notice this changed to 25. It's no longer running. Stop button will stop an infinite loop in Jupyter. Yeah, exactly. It's stuck in an infinite loop, so it never actually hits these print lines, right? So it'll never actually print anything. It's stuck executing this statement forever, right? These two statements, nothing else. So that's number one. The other way that you can do it is you can actually shut down your notebook entirely. Just gonna save it right there. So if you shut it down, it goes gray, which means it's no longer an open workbook. This kills anything that might be running inside of it. So you can reopen it and remember to fix the infinite loop. Bam. So if you've got an infinite loop running, and you're on JHub 2, it's not only your own it's not your own computer resources that you're hogging. You can also you're essentially hogging server time as well. So if you're in an infinite loop, please shut it down. Please don't just leave it running and like go and eat a sandwich and then come back and realize that it's still running. Oh, that's a good point, actually. So when you're working in a terminal environment, such as this one, boop, you can also like for example, while true. That's the easiest way to make an infinite loop, right? Oop. So this is now caught in an infinite loop as well. Generally speaking, and this is sort of a Linux thing, in order to interrupt something that's going on in a terminal, you hit Control-C. You can see in PowerShell this registers as a keyboard interrupt, and it reset my properties. It's no longer a big huge size. There, you can see we have that registers as a keyboard interrupt, which is very similar to an exception. So, I wonder if you could handle that type of an exception. Anyway, I'm pretty sure that you can do that within Jupyter as well. That might be an alternative third way of doing it. Control-C! Is it running? Is it in? Control-C? Maybe? Maybe it thinks that's copy. I don't think that works in Jupyter. You'll just have to use the stop button. Anyway, infinite loops are not an irrecoverable thing. Yeah. So, generally speaking, however, if you do this inside of a larger program, like, some other application that you're doing, in Windows, normally what you have to do is you have to go Control-Shift-Escape and get into Task Manager and shut down the program, right? But generally speaking, infinite loops are kind of a rookie mistake. So let's talk about something completely different, in the words of Monty Python, and now for something completely different. There's a way of converting things to and from various data types, and that is called typecasting. It works a little bit different in Python than it does in other languages. In Python, it's just a function call, using some specific function names. So, for example, I'll just do this in PowerShell. If you wish to create a float from an integer, there you go. All you have to do is use the float function. Note that the type of 4 was an int. If we have a string, right, the float interpretation of 4 is the same thing. So, thank you for the short... You're very welcome. Yeah, Control-Shift-Escape. I think it's... Pretty sure that's it. Yep, that's Task Manager. Boop. Close that before anybody can see my process IDs. Hack into my computer and shut it down. Ooh. So, if you have a numerical string, this can be basically read into a numerical format by use of these conversion functions. Now, here's a question. What do you think that, let me just simplify this. What do we think that integer conversion on this number will do? Please type your answers into chat. What's this going to do? Int of string 2.93662. And while you're doing that, I'll just demonstrate that there are some conversions which result in errors. So if you try to convert to a floating point, for example, bacon, you get a value error. So, could not convert string to float. Bacon. Bacon is not recognized as something that can be converted to a floating point number, which is probably correct. So, rather than attempt the impossible, the computer creates an error and halts execution. So, we've got 2. Yes. Everybody thinks 2. Some person thinks an error. 2.0. Floor it. Ooh, we've got some clever clogs in the chat. So, the person who said error is correct. The problem is that this is a string, but it doesn't have a direct interpretation as an integer. It doesn't pass it through float first, right? It's trying to convert that directly to an integer. So let's remove that, and then maybe we'll get the same answer that everybody who didn't pick up on the error will think. So what happens if you try to integer convert 2.93? You get 2. So the reason for this is a little bit complicated, but essentially, if you think of the number as being represented as a series of 1s and 0s, what happens when you convert from a floating point to an integer is it takes the part of the number that's representing the decimal component and it chops it off. It just gets rid of it, right? It's not a rounding operation. It's a truncating operation. It just deletes the information that it doesn't need. So in that sense, it's like, yeah, it's not a rounding operation. If you want a rounding operation, just call round. There you go. That's, and that's, probably the preferable way to do it. I bet you even get a integer from this. Yep. So some things have implicit integer conversion as well. Oh, I'm sorry. Could some of you not see the quotation marks? Oops. I don't think I can blow this up any bigger. Font. Raster fonts. Lucidia. Can I do big? Lucidia? Ooh, okay. There we go. I think that's better. Cool. We'll move away from raster fonts. So, I didn't intend to trick you. It's just convenient that it worked out that way. So I'll give you just a little bit of a taster of things to come. We talked about tuples, right? A tuple is something like 1, 3, 7, 2, 8. And I know those aren't the numbers that I was typing in. So t is equal to that. If you want to convert t to another format other than a tuple, like say a list, there's a explicit conversion function for that. Again, like we haven't really talked about the differences between tuples and lists, but this is a useful thing to know. Sets are also a thing. Notice it deletes the extra 2. That's a property of sets that we'll get to when we talk about sets, but just keep in mind that you can convert between things that are data structures as well in Python. It's very handy. There you go. Cool. So let's talk about if statements. I won't bore you with going through this thing again. However, we have a new one. And that's the if, elif, else. So if you want to create long series of if statements, you can create what are called elifs. It's like doing various cases. You can, let me do a thing here. If, for example, you say if x is equal to 3, do whatever. Elif x is less than 2, less than 1, do something else. However, implicitly what's going on is it's x is not equal to 3 and x is less than 1. That's the real condition. This part is what's called implicit. It's not explicitly there. It's not, in black and white. It is assumed to be the case. Why is round 2.5 result in 3? I thought it would be 3. 2. Okay. Let's see here. Let me see if I remember how to do this. It's for floating point reasons that we'll get into. Basically, the way that this is being represented in floating point is something like that, right? And because it's not quite, one, basically the 2.5 that you're typing here is not really 2.5. It's a very, very close approximation of it that exists only in floating point representation, and as a result, it's not actually 2.5, so it rounds down instead of rounding up, although it could just as easily have rounded up. Floating point numbers are notoriously imprecise. So, yeah. But we'll be talking about that in slide set 5. Oops, I just closed PowerShell. Here. Okay. So, where were we? So, basically, if you want to do more if statements on the not true branch of the original condition, you can do these with elifs. In other languages, this is less abbreviated. It's written as if x, if some condition, do something, else if some other condition, do the other thing, and else, do some third thing. Yes. Yeah, that's the mysteries of floating point. 2.5 rounds down, but 3.5 rounds up. Again, wait for slide set 5, guys. We are going to get into it in all of the nitty-gritty. You will understand. Just, I have to get through this this set of things. Oof. Okay. All right. So, here's a question. Let's write a function that determines whether a number is even or odd. Let's do this in Jupyter. All right. So, delete you. Goodbye. Define is even, or do you even. Can't use that, but I wanted to name it something slightly sarcastic. So we take some number n. I'm sure chat will have told me by the time we get there. How is it that you determine whether something's even or not? What's the easiest way? You can do it in a single expression statement, or in a single Boolean expression. Determine if something's even. So, modulus. Very true. So, n mod 1. Sorry, mod 2. If something is divisible by 2, then it's even. If it's not divisible by 2, then it's odd. So, if the modulus by 2 is equal to 0, then it's even. If the modulus by 2 is equal to 1, and that's the only other thing that it could be, then we can return odd. Very simple. Yes. Mod is extremely useful. I highly recommend putting it in your bag of tools. Generally speaking, the way that I like to view this course and all of these lectures that we do is every time I show you a new thing, I want you to think of it as a tool in your tool belt. So modulus, you can whip that out in any occasion where, you need to know if something's repeating, or you need to know if something's even or odd, or you need to know something about something like that. Something involving divisibility. Generally speaking, it's sort of a pragmatic view. Anyway. So, there we go. Here we go. Even, odd, n. If n modulo 2 is 0, return even, otherwise return odd. And of course, we can test our function. Test our function. Do you even 3? Nope. How about 7? Nope. 10? Yep, that's even. There you go. How is 1 the only other possibility? Good question. So, actually, this might be a... You know what? I'm gonna write you a program and demonstrate to you. So, for x in range from, you don't have to write the 0 if it's from 0 to something. So from that to 100, let's say. Or you'll get it after 10, I think. Print x is equal to, geez, all right, plus string x. There we go. Print x mod 2 is equal to plus string interpretation of that guy there. So, did you get that? What if we put in a float? Don't worry about that. Integers only. But as you can see, the values are alternating between zeros and ones. So if it is in fact integers that you're dealing with, assumes integer input, then the only possible values are 0 and 1. Because, 5 divided by 2 is 2, remainder 1, remainder is 1, 6 is 3, remainder 0, etc., etc. So, it's modulus 2 is equal to 0 is just testing. Like, when we calculate this, it's testing to see if it comes out to 0, right? And if it does, then it means that the number is evenly, perfectly divisible by 2. So it's divisible by 2 with no remainder. If any number is divisible by 2 with no remainder, that number is definitionally an even number. Yes. Hopefully that answers your question. Good. So, write a function that determines whether a number is divisible by 2, 5, or 10. What does this program output? So, we're just going to, I'm going to spare you the agony of me implementing these by hand. And the purpose of this is to demonstrate how the program flow is different if it's else ifs as opposed to regular if statements. So, if n mod 2 is equal to 0, we return by 2. Else, if n mod 5 is equal to 0, return by 5. Else, if n mod 10 is equal to 0, return by 10. Print divisibility of 5 plus the divisibility of 10. So, cool. What's this going to output? Who can tell me what this is going to output? Is there an A and B on this? Yeah. Yeah, I don't see any letters here. Oh, it's on the next slide. Jeez, okay. Sorry, guys, there are letters. Oof, okay. So, the answer to this is A, by 5 by 2, as a number of you have pointed out. The reason is, when we call divisibility on the number 10, although this case here would seem to be made specifically for the case of divisibility by 10, in fact, divisibility by 2 gets executed way before that would ever be hit, right? The first thing that it tries is mod 2. Since 10 itself is divisible by 2, this is the numerical property, anything that's divisible by 10 is also divisible by 2. So, nothing that's divisible by 10 is going to actually hit n mod 10. It's never going to hit that comparison. It's always going to be it's always going to hit the n by mod 2 line comparison first. And since it is the nature of return statements that once the first one inside of a function is hit, that terminates execution of that function, we're never going to see how the rest of the comparisons come out. So there you go. So how about now? Given the time delay and the fact that we have a reasonable amount to move through this lecture still, I'm going to spare us the agony of, re-quizzing for each one of these. So if we modify it such that we swap the positions of the mod 10 and the mod 2 test, obviously in this case we would get by 5 by 10, because divisibility 5 would first hit this mod 10 check, that would fail, it would go on to this one, it would return by 5 for the first one, and then the second one, it would hit this first case and return by 10. Would I do an if or a statement then? I don't know what your question means. Sorry, Matthew. I am having trouble parsing your question. So An alternative way of doing this uses nested if statements. So in the case where we have divisibility by 2, or divisibility by 2, we then check to see if we also have divisibility by 10. If we do, then we return by 10. Otherwise, we return by 2. So in this particular case, we would also get by 5, bump, 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 by 10. So, and of course, for our final variation of the divisibility, we can also have compound conditions. So if you remember, if you guys remember back to the Boolean operators slides that we had in previous lectures, the Boolean operators can be used to join things together. So if we have the mod 2 check and the mod 5 check at the same time, then whatever in order to get by 10, it has to be divisible by both 2 and 5. Since those are both prime numbers, then that obviously means that we are checking essentially for divisibility by 10. So to answer Matthew's question, in this particular case, we're not looking for an OR statement here. I'm just trying to put myself back into the context of 2 slides ago. So the backslash is to indicate that the previous line is it's to indicate that these two are the same line, like print divisibility 5 plus that. That's to indicate that they're the same line. I'm going to tell the TAs to not do that anymore and try to fit everything on one line if they can. So what you would get if you put the divisibility by 2 and the divisibility by 10, like if you'd had n mod 2 equals 0 or n mod 10 equals 0, you would still fall through to by 2, right? That doesn't change the flow, since anything that passes a mod 2 test is also going to pass a mod 10 test. So with respect to adding an OR in this situation, it wouldn't, again, it would not make this more exclusive, right? If you add more conditions and they are bound together with OR operators, that makes your condition more permissive. More things can get through the condition. In this particular case, we're simply, it's an ordering problem rather than anything specifically to do with the conditions. Hopefully that answers your question. So, anyway, this program outputs by 5 by 10. Because even if, for the example of divisibility 5, even if one of these conditions comes out true, the other one comes out false. False and true is false. So that falls through that condition. Hits that one, fails on that one, hits that one, and that's the one we keep. Does it make it more efficient because if a number doesn't pass the 2 test, then it doesn't have to run the 10 test? Yeah, I guess. If Yeah, because in this particular case with the nested if statements, if we like versus this one, right? Or, well, I don't know. It's not more efficient than this one. This gets it in one statement, right? It, like, assuming that this worked, which it doesn't, but assuming it did, you would need 3 comparisons to hit this one, right? But in this one, you only need 2 comparisons and then you get to it. So, but, this one also doesn't work. So this isn't really a efficiency problem. So probably not going to get through all of this, but we'll try. I mean, before the break. So, Spectre. This is like an application type thing. So, there was, a number of years ago, a bug known as Spectre. It was a security vulnerability in most Intel and AMD CPUs, which, if you know anything about the chip market, then that's like the overwhelming majority of that. It's like that plus ARM, and that's the entirety of the microprocessor industry. Although, well, I won't get into it. Anyway, so Spectre, we're gonna go through the sequence of coding events which could expose this vulnerability, and it's interesting because it relates to if statements. Generally speaking, there were 3 components in the Spectre vulnerability. Number what? Yeah. Ooh. Yeah, essentially. Basically, all CPUs had this vulnerability. Number 1, branch prediction in if statements. Number 2, memory caching. And number 3, timing. Timing is everything. So let's discuss what branch prediction is. This is like a technical subject, and don't worry, it won't be on the test. This is mostly for interest's sake. So, generally speaking, modern CPUs have the ability to do multiple things at once, often because they have multiple processing cores, right? Back in the old days, you had one CPU core inside of your computer, and it could execute one statement at a time. That was it. In our modern iteration, we have multiple cores in CPUs that are all trying to speed things up and do things in parallel and do everything nice. So, sometimes, as a step that makes things faster, the program will do branch prediction. That is, it will try to calculate what the results of if statement branches will be based on a calculated result that hasn't happened yet. So it basically says, well, I can make this quick calculation or load that data in anticipation. Yeah. Don't worry, the Spectre vulnerability doesn't exist anymore. Thank goodness. However, you'll be absolutely thrilled to know that when we get to SQL, we have a whole 3 or 4 slides on how to do SQL injection attacks, which are actually one of the most prevalent and dangerous types of security vulnerabilities on the internet. A lot of the big data breaches are due to SQL injection attacks, which basically, if people don't check the stuff that's executing, then people can include programming code in with database entries and get the computer to execute those as if they were, intended operations. And, anyway, we'll get to that. That one's slide set 11, I think. We'll talk about SQL. It's lots of fun. Anywho, so essentially what would happen, if you had some operation that takes a long time. Like square root, for example, takes actually a reasonably long time to actually calculate. You can predict what branch you're going to be headed down, do some stuff in that branch in anticipation of the result that's coming down. So if the branch prediction ends up being wrong, the CPU basically rolls back it rolls back everything that was inside that branch of the if statement and continues on with the other one. Those two slides are the same. So the Ooh, computer file. I'll have to check that one out. Sounds like he might be related to the number file people. Anyway. So that's ingredient 1, branch prediction. Ingredient number 2 is memory caching. So this is your classical von Neumann computer architecture. You've got your input, you've got your output, you've got your central processing unit, and you've got your memory unit. So a cache is a special type of memory that's used to speed up the execution of of everything, really. Memory is, generally speaking, in terms of there are lots of different types of memory inside of your computer. Generally speaking, with memory, the trade-off is the more permanent the memory is, the longer it takes to access. So if you think about your hard drive, extremely permanent memory, so permanent, in fact, that it can survive the powering down of your computer, which at the time that was invented, believe me, that was like, wow! Memory that's persistent past power down? Is that even possible? Turns out it was possible. Sort of in the next level up from that, you get random access memory or RAM, your RAM chips. This is less permanent memory, so it degrades faster, but it's faster to access. So this is more useful for loading programs that you're currently executing into. The next level up that you have is cache. So cache memory is where you store things that you need, like, relatively frequently. Things like the variables that you're assigning inside of a Python script. Stuff like that, that would go into cache. So again, cache degrades relatively quickly. It degrades even faster than the RAM, but it's smaller. Some of it can even go on board inside the CPU itself, and it's a lot faster to access, which speeds things up. So the cache is the cache is used to store recently used values. So yeah, basically loading from cache is faster than loading from main memory. So stuff that's used recently, you keep it in cache so that if you need it, you can refer to it quickly rather than have to go all the way back to the main memory for it. So the problem, and let's see, how many more slides do I have? Okay. You know what? I'm going to finish Spectre and then we'll take the break, okay? So, generally, I use the phrase generally speaking too much. So, the nature of this vulnerability was that the branch prediction that these CPUs were calculating was being stored into the cache. So, if a if statement predicts the wrong branch, that wrong branch information is in the cache. But the vulnerability was when the CPU rolls back on wrong branch prediction, it didn't roll back the cache. So the cache remained, the cache kept that old information. Or this, it's not old information, it's like unused future information that ended up not being necessary. But anyway, so the third ingredient of Spectre was timing. If you managed to load data from that cache that was, while it was in this state, before the cache gets reset, because the cache gets, rolled over every once in a while, before it gets reset, but after this wrong prediction had been made, then you could actually read that data out of that cache. So, yes. So in this particular example of it, the load to data operation takes a different amount of time depending on whether data 2 is in the cache or not, right? Obviously, if data 2 is in the cache, it'll take less time. And if, like, this would be operating on the assumption of the else branch being the branch that would have worked. So, if an attacker program attempts to load the data from data 2 while it's in the cache, well, first of all, it has to share the memory cache with the victim program, but what it can do is it can, yeah, so it's kind of complicated. The attacker program can measure how long it takes the victim program to load that data, and as a consequence, it can infer what the victim's value of y was here, so what the result of this function was. And as a result of that, you can actually access data, right? You can get, like, if the value of y was, for example, is this password correct, or, something like that, it was a security breach. You could find information out about the inner workings of another program from outside that program. Generally considered a bad idea. Anyway, that's the Spectre attack. When we resume, we shall be talking about linear search, so we'll be talking about some algorithmy type stuff. See you in 6 minutes. Ha, gotcha. You thought I'd forgotten to do the thing again, but I only pretended because I was being sneaky. I should check to make sure that I was actually on the mic there. Ah, good. Oh, there we go. Funny jokes, funny jokes. Anyway, so linear search. Generally speaking, when you start getting into the algorithms and data structures materials, one of the very first topics that you'll be talking about in any computer science program is searching. Searches and sorts, those are the two big ones. So a search is where you look through a sequence of values to find the first occurrence of some value that's been specified. So anyway, we're gonna be talking about linear search, which is, you know, a reasonably straightforward thing to do. So, example application. Actually, we've already talked about this with respect to when we talked about strings. You know, the find index of function. That function is a search function, obviously. It searches for the value that you specify. However, rather than return the presence or non-presence of the thing that you're searching for, it returns the index of it. So, yeah, index. So, let's try to implement it. Let's go back to Jupyter. So, def, lin search. We have to have some data structure, so let's just use a tuple. Incidentally, when you're programming in Python, generally speaking, the data type of the thing that you're intending your function to be used on, the data type of the argument, since it's not specified explicitly, it can be a lot of different things. And it's interesting because a lot of functions will operate across multiple different data types. So a function that you wrote specifically for a tuple might still work on a string. Or, well, it especially might still work on a string because strings and tuples are very, very similar in terms of their properties. But it might even work on something like a list. But, you know, parenthetical note. So, we have a tuple, and we also need something we're looking for, let's say eat. So there are a couple of ways to do this. I'm going to use a for loop for x in t if x is equal to e, return true. And if that manages to execute that all of that loop without returning true, you return false. So this is in the case that the search has failed. Cool. So just to demonstrate that it works, if we lin search for in 1, 2, 3, 4, 5, we look for 6, we get false. If we look for 2, we get true. There you go. This is another implementation using a while loop. So I can see that there is an error in this slide. This if statement, it needs to be indented. Yep. Okay. Question 1 solution. Question 1 of what? And also, this is the lecture. If you're looking for the answers to assignment questions, you should allow the TA to tell you no in the tutorial. So this is Let me just copy that. This is what it's supposed to look like, folks. Oh my gosh. Actually, that doesn't even make any sense. Oh, wait, no, I know what they're doing. Okay. Never mind. You know what? Your professor is dumb. I realize now the error of my ways. So, this is what it's doing, this particular one. It's using, in comparison to the way we did things here, where we have an explicit test for x being equal to the element we're looking for and returning true in that case, we're actually stopping the loop executing if the element at the address that we're currently looking at, or at the index that we're currently looking at, is equal to the element that we're looking for. So, basically, this thing counts up until either it hits the end of the loop or it hits the value it's looking for. At that point, the loop execution stops. If I is less than the length of s, then we know that we exited this loop via this condition. But if I is equal to or greater than, it won't be greater than, but if it's equal to the length of s, then we know we exited on this condition, so we return false. So this is fine. A variant which returns immediately looks very distinctly like our version of it, but with a while loop instead of a for loop, because, you know, for loop is the next section. You can just click through. Ha ha ha. Very cool. So, that's cool. Generally speaking, I think that this is better. It doesn't make a lot of sense to me to have two conditions on a loop and then have to determine post-fact which one of the two was the one that you exited on. That just doesn't make a lot of sense to me. So, here's another keyword for you. There's another tool for your tool belt. You can use the break statement to stop the execution of a loop and jump to the next statement after the end of the loop. So it allows you to end a loop. Break allows you to end a loop. Continue, incidentally, allows you to end the current iteration of the loop and jump to the next one. So, in this particular case, applied to this particular algorithm, we have the worst of both worlds. We have the somewhat more convoluted structure of linear search 2, where we're returning things mid-function, which is like, you know, it's okay, but we don't prefer it. And the, you know, having to keep track of what the condition was you ended on and return things on that basis from linear search 1. We combine both of those by just having the program break if this condition comes true, rather than just simply returning I, and as a result we exit the loop, go to the if statement, and test to see which condition we exited on. Question: if you have a function that returns true and then the next line returns false, would the function return true or false? Good question. Let's see. Def. Return true. Return false. Oh, I have to actually call the function. There we go. It returns true. Won't a loop end on its own as long as it's not infinite? Yes. However, sometimes it's an efficiency thing. So I know, like, people have been asking about efficiency, and I've been largely saying, well, yes, but also no to most of it. It's like, efficiency, you know, technically speaking, this has fewer statements, but it's not a significant contributor to overall runtime? Loops are a significant contributor to runtime. So if you have well, actually, linear search is a fantastic example. You could definitely design an algorithm such that it just continued going through all of the rest of the elements that after it found the element that it's looking for. You could totally do that. In some applications, that's what you would want to do. Like, for example, if you were counting the number of that element that there were inside the data structure. However, if you're only looking for the first one, once you've found the first one, it doesn't make a whole lot of sense to execute the rest of the loop. You're wasting valuable CPU resources. So you can imagine if, for example, like on these types of toy examples that we have in the slides, it's relatively trivial. You know, it's only like if your element is the 7th out of 10, then you are only saving 3 cases. But what if it's the, 700,000th out of 2 billion? Because you can apply the same code to both situations, right? But if you stop looking once you've found what you're looking for, you'll vastly improve the best case and average case program execution time, which has an increasingly pronounced effect the larger the data you're operating over is. So hopefully that's an answer to your question. Something resembling an answer anyway. So there you go. That's linear search. So let's talk about for loops. For loops are the best loops. You should use them, not while loops, whenever possible. So for loops are another type of loop structure. They are syntactically almost identical. Well, actually, no. They're reasonably different syntactically. Semantically, they do very much the same thing. So what they do is they iterate over all of the elements of a tuple, a string, a list, a dictionary, a set, anything iterable, a range object. Unlike while loops, the number of iterations in a for loop is always bound. So it's impossible, asterisk, for a for loop to get into an infinite loop. So this is where I ask all of those clever clogs in chat, can you guys construct a scenario in which a for loop still gets you into an infinite loop? Because you see at the bottom here, really talented programmers can always get into infinite loops. So here is an example. Both of these algorithms do the same thing. In the while loop version, we have s, the string potato, I is equal to 0, while I is less than the length of s, c is equal to s at I, print c, I plus equals 1. So the issue that we have here, this statement is redundant. It's because you can just take si and put it in the print. So let's consider this as having 4 statements here, not including the definition of potato. So on the for loop side, for c in s, for character in string, print c. See how much more compact that is? Potato. Yes. Okay, I've got some answers in chat. So if you have a function that returns true and the next one is... Oh, that's... Yeah, I answered that one. For loop with nested while loop. Yeah, that's true. But that's not what I'm talking about, man. Come on. No. That's cheating. That's cheating. Yes. Konstantinos, you've got the answer. That's right. So in Python, the for loop iterates over a data structure, right? So if that data structure is changed while it's being iterated over in a particular manner, you can actually create an infinite loop using a for loop. Specifically, if you add elements. If you keep adding elements to the thing that you're iterating over, like take a really obvious example. Let's say for every iteration over the data structure, you add 2 elements to it, right? Obviously, you'll never reach the end of it, right? Because the data structure is growing faster than the loop can process it. And I realize you can't see my hands going because, yeah, anyway. So that's one way in which you could do that. Elongate the potato, yes. Yep. So when range is infinite. So in order for the range to be infinite, you would need a infinite data structure. As far as I know, Python does not support theoretically infinite data structures. Haskell does. Haskell has infinite data structures, but it only gets away with it because it does lazy evaluation. So the compiler, processor, whatever you want to call it, the Haskell compiler is smart enough to not process anything that it doesn't need to get the result that it's looking for. So it'll use as much of that infinite list as it needs to calculate the result and just ignore that the rest of it exists. So it's infinite, but, you know, there you go. Anyway, for loops. This is very important. The body of the for loop should not modify any variables. Should not modify the variable. I'm not sure why it's n. There's no n on this slide. Anyway, if, for example, I can whip one up real quick here. For c s is equal to potato, for c in s, s is equal to s plus exclamation point, print s. Oh, interesting. Oh, okay. Oh, right, because s is, okay, so the reason this one didn't work is because s is a string, and strings are an immutable data type. If we do it on a mutable data type, that should work. So if we convert it to a list, which is a mutable data type, come on, parenthesis out of completion. There we go. And if I add this as a list so the type is compatible, what? Come on. Anyway, maybe they anticipated this. It's possible. What about, how about, okay, now I'm just trying to break things. s.append. There we go. Ha! We broke it. Congratulations. Good. I mean, it's a really good game, Portal 2. Portal 1 is arguably better, but that's like, yeah, it's still really good. Anyway, So in this particular case, we have gotten some crazy weird errors. The notebook server will temporarily stop sending output to the client in order to avoid crashing it. To change this limit, blah, 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 blah. So I broke it. Hooray! I broke it. So there you go. Oh, yeah, it's because concatenation is it's an immutable operation, and append is a mutable operation. It's got to be mutable to be able to do that. Portal 2 is better in terms of it being longer, and like the jokes are maybe a bit better. But Portal 1, like as a video game, there is no wasted space. You know, every single part of Portal 1 is like there's no fluff whatsoever. It is a tight, compact experience. But anyway, so is that what the last hour of lecture is going to turn into every night? Us just talking about Portal all night? Anyway, so it's also possible to iterate over a range of numbers. In Python, in for loops, we have, well, not just in for loops, we have this very handy range object. So it's kind of tricky to show because if you try to print a range, you get something weird. So just print range 20. Oop. Really? Stop it. There. It shows up as a range from 0 to 20. In order to see what's actually going on, I think list conversion works on it. Yeah, you can convert it to a list. So you can see we've got from 0 to 1 less than the number that we put here, range object. So we can use these to create data structures on the fly. So that we can use the for loop. The for loop has to have a data structure. So if you don't have one, you can create one by using range. Matthew asks, will the end result of this course allow us to change our grades in Mosaic? Only if I accidentally enter in my password on stream and it doesn't have the asterisks over it. Although, to be honest with you, Mosaic is such a dubiously implemented system that it wouldn't surprise me if you managed to find some way of hacking into it. Actually, at one point, my supervisor, who's now the department head, was refilling his meal card, like the campus meal card, through Mosaic, and like somehow had his credit card information stolen, like because Mosaic was so terrible at protecting that sort of thing. So, like, I don't know if anybody here has ever used Mosaic to like entered in credit card information into Mosaic in order to like pay off your tuition or whatever. I wouldn't necessarily recommend it. Perhaps you should like set up a payment order thing on your online banking instead. That's a lot more secure. Or at least it was years ago. They probably may have fixed this vulnerability in it by now, but they probably did. But then again, you never know with these sorts of things. Anyway, is that what SQL injection is for? We will talk about SQL injection when we get to SQL injection. Something to look forward to. Is everything in Python 0 indexed? Indexed. Yes. Tuples, 0 indexed. Lists, basically anything with a numeric index is 0 indexed. Yes. Yeah. Yeah, always clear your cache. Yep, very true. Cache problems. We were just talking about cache problems. So, yeah. So another thing to note, actually I think this is a mistake in the slides. it says that the loop variable is undefined after the loop, but we're going to test that. So for I in a range from 1 to 10, print I, then outside the loop, print I. It still worked. Ha! Maybe that was applicable for Python too. Yep, 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 yep. That's a good one. I like that one. Cache problems are cache problems, but they become cache problems. Yep. So, there are a couple of ways that you can use the range object, and it's kind of a non-intuitive thing, Anaconda. I want my PowerShell back, thank you. Why do you always reset? Stop it. Just stop it. There. Okay, Python. So the range object, again, if you just print it, doesn't really do anything. But there are some interesting things that you can do with it, which you should be aware of. So first of all, be aware it starts at 0 and it goes to 19. That's because the thing is designed to be the indexes of some 0-indexed data structure. Indexed. It's difficult to. That's a difficult word to say. Indexed. Anyway, not enough vowels. So you can specify what the range is. If you have just one argument, it goes up to n minus that number. If you include 2 arguments, it goes from the first one to 1 minus the second one. So 7, 8, 9, 10, 11 in this case. Cool. The third thing that you can do, which is neat, is if you've already got 2 arguments going on, you can add a third and tell it what to count by, which is kind of fun. Notice that although we're counting by 2s, we don't count 20 here, right? Because it's n minus 1. And also note that when we're counting by 3, basically it stops at the last one that's still inside the range, but when you're counting by it. And it always starts from the first one. So there you go. That's some cool stuff. That's essentially all of this stuff on this slide here. So, yep. Generally speaking. This is cool because this is also this is the same format as slicing. So if we have list range 30, we can index that by using the exact same, there we go. You can produce the exact same you can produce the same sequences of numbers that you could produce by giving these parameters to range as you would by giving those parameters to a slicing operation. They actually operate in exactly the same manner as slicing. So slicing is something we're going to talk about reasonably in depth on Wednesday, but this is just something to be aware of. Okay? Basically, the rule with slicing is the same as the rule with ranges, except you go you use colons instead of commas. What about minus? Doesn't it count backwards? Yes, actually it does. So if you include negative, this is a cool thing about indexing. So, and it's a thing that pretty much only Python does. If you start including negative indexing I'm just going to print the range so that you guys can see it. Negative indexing will start counting from the back. This is a thing that, as far as I'm aware, only Python does, but it's kind of cool. Another cool thing is that you can easily reverse a list by counting by -1. And when you leave these parameters blank, you're saying go from the start of the list to the end of the list. And -1 as a step means, you know, counting backwards. I wonder if that works on range as well. Let's check it. So from 0 to 10, -1. Nope! So that doesn't work on range. Be warned. Cool. So, the range object, is there anything pertinent on this side? Oh, yeah, we can convert range objects to a tuple by conversion. I've been doing lists because I like lists, but you can also do tuple because you can. There you go. The difference between tuples and lists is going to be almost purely academic until Wednesday. So, here's an example. If we wish to print a list of even numbers, well, we can do it in even less time than that, can't we? But n is equal to 50 for x in range 0 to n by 2, print x. We can one-line that. Come on, guys. List range 0 to 50 by 2. Padoom. There you go. Oh, so to answer your question, I don't think that it would work, actually. So the question is, so what if you started with 10 and went down to 1 and you were counting by -1? Oh, yeah, there you go. Actually, that works. Okay, never mind. That works. Thank you. Yeah, so obviously, like, okay, if you're counting from 0 to 10 by -1, at least it didn't get us into an infinite loop, because I've got the bounds reversed and could have easily. Anyway. So, yes. So let's return to our factorial example that we were discussing at the beginning of the lecture. Before, if you remember, we were doing this with while loops. Well, we can also do this with a for loop. So, in the case of the for loop, we still need an accumulator, but all of the indexing is taken care for us by our declaration of the range object. So we're counting from 2 to n plus 1. Remember the n plus 1 problem that we had? There you go. Actually, it's interesting. Is this like almost exactly the for version that we did? Yeah, it is, except I'm counting from 1 here instead of 2. There you go. Ta-da! We were right. So, here are some common errors that you may often find when you're programming loops. Some of these result in infinite loops, some of these result in incorrect answers. So, number 1, incorrect initialization, particularly that of the accumulators. If you initialize them incorrectly, they start off on the wrong foot, and nothing that they do will be correct. If you remember that issue that I was having with my implementation of Factorial originally, that could have been solved by correcting the initialization. Initializing it to 1 rather than initializing it to n, for example. incorrect termination of the loop. So sometimes if you're one off of the index, you can sometimes even try to access data that doesn't exist. But generally speaking, many of the errors that occur in loops have to do with where you have the condition, right? Or what the condition is comparing. So, for example, if I am, oh my goodness, how about here? Well, I don't know. Let's see here. Do I have an example with a while loop and a data structure? Nah, I don't think I do. Anyway, basically, just be careful that you're not trying to access stuff that doesn't exist. Infinite loops can be created by incorrectly updating the loop variable, or a number of other things, expanding the thing you're operating on, even though, well, yes, I did get that to work. Index calculation that is off by 1. That was another error that we saw in the Factorial implementation that we did, that first one that we did. Improper bracketing and indentation of nested structures. You always gotta keep in mind where the indentation should be. In Python, it's important. In a lot of other languages, not important, but in Python, it's important. So, here's a function that counts the frequency of, oh my goodness, like the one slide that I needed those to pop in on. Anyway, so this is a piece of software with some bugs. And ordinarily, I'd ask you how many bugs there were, and the answer would be 3, except they are already highlighted, so there you go. That's disappointing. This is always a fun example. But we can still do it this way. We can fix it. So here. Oh. Sad professor noises. So, here it is. There are 3 errors in this. Number 1, we've got greater than or equal to the length of this thing that we're counting over, rather than just less than. If it's less than or equal to, then you will be executing I when it's equal to the length of the thing that we're iterating over, which means that you're trying to access a index value, a value at an index that doesn't exist. That's a problem. So that's what you do. Next, and this is kind of a tricky one, we have this problem here. So the thing that updates I, that needs to not be gated by an if statement. So this piece of code would actually only terminate in a case where every single element of this of sequence seq passes this condition, which means that the only thing that would terminate is if the thing were composed entirely of n's. So we want to delete that right there. So that's number 2. Number 3. Number 3 has to do with x. We see x equals x plus 1 here. However, x is never actually initialized. So if we try to run that, we'll actually get an error rather than an infinite loop. unbound local error. So local variable x referenced before assignment. So it's like, you want me to add 1 to x. I don't know what x is. This is the first time hearing about x. So what you got to do is you got to say x is equal to 0 up at the top. You got to initialize your variables. And then it doesn't complain. It just gives you the answer. There you go. So, and this is our last slide for the evening. The rest of the evening will be filled with Portal references and discussions of various video games. Just kidding. I know you all have tutorials to get to. So, for loops, the whole deal with for loops is that they automatically initialize and increment the loop variable, so you avoid a whole bunch of different types of errors. However, a for loop might require you to get out of the loop using return or break, and thus, you introduce multiple exit conditions. While loops allow a single exit condition, there's a spelling mistake right there, and make the terminal condition explicit. So this is basically a justification for how the slides had organized the linear search example. For this reason, we avoid break and prefer a single return at the end of a function, but don't worry about it if it's, generally speaking with this course, as long as it's working, that's the main thing. This is a stylistic point more than anything. So there is one thing that I want to go over kind of explicitly here. A few slides back, actually. So, with respect to this example, notice that in the case of the for loop, C is the element, each element of S sequentially. In the while loop, C must be assigned to each element of S according to the index I. So basically, in the for loop, C is equal to Si is implicit. It's a thing that automatically happens. So, and as you'll see when we get into more complicated data structures, for loops do not have to necessarily just iterate over things that are indexed numerically. They can also be indexed. They can also be things like dictionaries, which might have anything as a index, or they might be strings which don't have indexes. All kinds of interesting things. But it's very, 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 very important to recognize the distinction. C is sequentially each element in S. I is just a number that points to an element in S. But yeah, anyway, I don't know. That's the end of the presentation. So I suppose if anybody has any questions for the professor, now is the time. I will now answer your questions in chat. Okay, so I have a coding-related question, which I will answer first. How do you write the last example of counting n in as a for loop? Last example of counting n. This one. Good question. I like that question. Very good, very good. All right. So, it would be relatively easily, actually. So, it's also here. Def count n better sequence. X is equal to 0 for element in sequence if element is equal to n, x is equal to x plus 1, return x. Yeah, it only prints the most recent one. So there you go. So notice that basically, like, sequence is already a data structure, right? So we don't need to create one with range. All we have to do is iterate over the existing data structure, and you can see we saved a few lines of code, and this will be more durable when it comes to the types of things that you can put in sequence as well. So, for example, this works with a string, but count. Let's try a set, which is a thing that we'll be talking about next week. I think this works for sets. Maybe not. Nope. Just make it a list and convert it to a set. That's the easiest thing. Yeah. So if you try to do this on a set, sets can't be indexed, right? Which causes a problem. However, if you try to do the same thing on this one, and let's just, throw an n in there so that it has something to count. We don't feel like it's utterly pointless. It actually works because the for loop is agnostic of the data structure. Since you're not assuming that the data structure is something that can be numerically indexed, then it doesn't have to be one. So yeah, hopefully that answers your question. As to Michael's question, how was my day? Well, it was pretty productive. In the afternoon, I had a stroke of inspiration with respect to the first test. So I got probably what will end up being the majority of the questions for the test 1 banged out this afternoon. Which is nice, because I always like getting things done a little bit in advance of the deadline. So, as for what's on the test, I guess you'll just have to find out. However, I can guarantee it'll be kind of cool. Some people will dig the test question, and that's all I'm saying. Are there any other questions? Why don't I use Linux? I set up OBS on Windows, and I just never... Like, all my configuration stuff for, like, the fancy synthwave background stuff is in the OBS thing on the Windows. Oh, I should say I dual boot Linux and Ubuntu, actually, and Windows. Ordinarily, I use Debian, but at the time that I bought the laptop, UEFI had just come out, and for whatever reason, the Grub distribution that had come with Debian at that time wasn't handling it well. So I just sort of said, screw this, I'll just use Ubuntu like a pleb. But, you know, not that Ubuntu is for plebs, but, you know, among Linux users, it's like, well, I don't know. A friend of mine said that, you know, if you don't use Ubuntu, then you're just a hipster. But using Linux is kind of a thing for hipsters. So I have a question. When and how long is the test? An excellent question. The test is on Saturday, the 23rd? It's in the syllabus. Let's see what the I also have it written on my calendar. Give me 2 seconds. Yes, Saturday the 23rd. I always trust things I read on a calendar more than my own brain. So, this is how the test is working. 9 a.m., Saturday, May 23rd. The test becomes available on both Jupyter Hub and Avenue. You have 24 hours precisely to complete the test. So the test is due at 9 a.m. on Sunday, May 24th. I do not expect you to take 24 hours to do the test. However, you know, I don't know what people's schedules are like. It's a take-home test, you know. I hope to design the test such that it should take you a couple of hours. So, but yeah, and of course, if you have a SAS accommodation related to test writing time, then you receive that according to the number of hours that the test is assigned for. So, yeah, hopefully that answers your question. Yes. Arch Linux, eh? Yeah. That's one of the hard ones for those of you who aren't. Can we MCAT the test? You want to get out of the test by writing a much harder test to get into medical school? I'm assuming you mean MSAF. Yes, there we go. Yes. However, if you choose to MSAF the first and probably easiest of the tests, your exam becomes worth 40% and your second test becomes worth 20%. Something like that. Yes. 10% of it goes to the exam and 5% of it goes to the other test. So, no, I didn't see. Yeah. It was just funny. It just came out funny. That's all. So, yes, you can MSAF if your, you know, if your good typing hand is crushed in a freak corn picker accident, then yes, you can MSAF. But, you know, yeah, anyway, that's the MSAF policy. Anywho, I can tell you that probably a number of you should be, all of you, should be switching over to the tutorial streams now. So I'll stay on the line as long as there are people still chatting, but for most of you, have a good evening. Enjoy your tutorials. When does the tutorial start? It starts at 8:30, so they start in about 5 minutes. Question about the test questions. Are they more difficult than the ones in the assignments? Assignment 1, certainly, but assignment 1 is pretty easy. It's like pretty intro to everything sort of material, so, generally speaking, I'd say that's more in line with the difficulty of stuff on assignment 2 and 3-ish, beginning stuff. Yes. The questions are designed to be, I don't know. Maybe slightly more difficult. Yeah, maybe a bit more difficult. Because, you know, it's a take-home test, you know? So, it's, you know, it's also a lot shorter than an assignment would be. I'm not going to tell you how long the test is, or how many questions there are on it. But, yeah. If you MSAF the second test, would that increase the weighting of the first test after we've written it? Yes. Yes, it would. But it would also boost the exam more than that, so yeah. Can you MSAF the exam? No. You may not MSAF the exam. The exam is an exam and therefore subject to the rules regarding deferred examinations as set out in the university's policy documents. So if you want to MSAF the exam, you end up with an incomplete grade until such time as you can make up the exam by writing the deferred exam sometime later on, which is probably a really stupid thing to do because you'll, you know, have forgotten a lot of the finer detail of the course by October of next year, probably. At least a lot of the stuff I'll be testing on. So, generally speaking, I don't necessarily recommend deferred exams. Like, if you're, like, physically incapable of it, sure, it's better than getting a 0 for the exam, but yeah. You exercise with caution, generally speaking. I should set up donations. I can't. I don't have... Okay, there are 2 requirements, right? I need 1,000 subscribers, and I need something like 4,000 hours of people having watched my videos. I'm making progress towards that, actually, but yeah, I can't set up channel monetization until I've reached those thresholds, apparently. And, you know, I kind of take the position with this that, like, I'm already getting paid for my services, so yeah. Yeah, Galaxy Brain move, yeah, for sure. So if you get 100 on the first test, you should big brain and MSAF the second one, so your 100% is worth more. Well, I mean... Yeah, but you're also taking a risk on the exam, right? Like, hypothetically, the exam is going to be the most difficult evaluation is going to be the exam. So, can we make subbot and view bots for you? I don't know, man. Like, to be honest with you, I'd prefer to not cheat to get it, just because, like, then the analytics data becomes kind of not necessarily informative anymore. Don't worry about channel monetization. I'm doing fine. Excuse me. Yeah. Don't go to the effort, man. Yeah. I could just drop the lowest test grade and make everybody's life easier. No. If I like, no. Used to be the policy to do that with assignments in this class as well, but no. See, there starts to be a problem of, well, why don't I just give everybody an A then? You know, like, you have to actually demonstrate. You have to actually demonstrate that you've picked up the material. And like, if you graduate my class without being able to write a for loop or an if statement, like, I have failed you and me and the university as an institution. So I will try not to pass people who don't deserve it. So I can't just give everybody the grade. If you want the grade, you're going to have to work for it. Well, I mean, 15% is already pretty friggin' low for a midterm. At least with respect to engineering programs. But anyway, I'm going to end the stream now because all of you should be watching your tutorials right now. So anyway, have a good evening, folks. Take her easy. Keep it real. See you on Wednesday.